Here's a quick introduction for JP and myself. If you have any additional questions, feel free to reach out to us. We'll do our best to get back to you. You can also find us on LinkedIn as well. But let's go ahead and take a look at what we're going to be covering today. So we've got three main topics that we're going to be spending most of our time on: ENVI workflows, temporal data cubes, and machine learning. We'll probably be spending about 10 minutes on each of those, and then we'll be ending right around 40 minutes, depending on how fast I talk. So with that, because we got a lot of content, let's go ahead and get started. So our first major feature on our agenda is the new ENVI workflows. These exciting updates to ENVI build off of the work we previously introduced in ENVI 5.6, which is the ENVI Workflow API. Using this API, and over the next couple of releases of ENVI, we're planning on consolidating and updating the existing workflows within the product. This will make sure users have consistent and modern ENVI user experiences, no matter what tool they use. The most exciting part about these new workflows is they make it very easy to turn the manual steps you go through into an automated process. We'll talk about the screenshots you see on the right here in just a minute. I've actually got a recording of a video walking through the anomaly detection workflow, which is what you'll see here. First, let's go ahead and spend a little bit of time talking about the four major workflows that we've got added to this release. So walking through each one very quickly, first we have the pre-processing workflow, which is all about helping you get your data ready for analysis. The great thing about this workflow is that in the future, we'll have the ability to add special logic for different sensors and data formats to help make sure you go through the right steps to pre-process your data and get it ready for analysis. Next, on the top right here, we have the vegetation analysis workflow. This allows you to do four different things: analyze agricultural stress, assess forest health and forest fire fuel, and perform simple vegetation delineation. In the lower left, we've added an automated image registration workflow. Keyword here is automated. This was not planned to replace the existing image registration workflow, but to add an entry point that makes it easy for non-ENVI experts to go through the steps to register images and generate an automated process from that. Lastly, we have anomaly detection. We're actually going to show a couple of videos here. We're going to take a closer look at vegetation analysis and anomaly detection, and then wrap things up with a little bit of detail on how you can take your workflows and turn them into ENVI modeler workflows. So with that, first, we have the vegetation analysis workflow. Here, we're using a PlanetScope dataset to go through and perform vegetation delineation. So we pick our data, we specify a vegetation index, and I'm going to pause the video here. And then we have an interactive step where we adjust a threshold for what separates vegetation from non-vegetation. So here in the video, if you look at my mouse, you can see I'm dragging the threshold around here just a little bit, just to call out and show how some pixels get highlighted and some don't. The default threshold here is pretty good for highlighting vegetation versus water or lake in this scene. So we're going to go to the next step. And once we get to the next step, this is where things get a little bit more exciting for this, where we can actually specify the classes and the threshold ranges for vegetation delineation. And here at the very end, we have a classification image that shows you where we don't have any vegetation, where we have sparse vegetation, or moderate or dense veg. And this is all based on the spectral index that you specify at the beginning for creating a mask. So as I said already, there's a couple of different ways that you can use this workflow. Just depends on the analysis step, what you pick and choose to do. The next workflow to show is anomaly detection. And this is a fun little example where we're using PlanetScope data to identify, excuse me, we're using PlanetScope data to identify icebergs in an image. Here we have the same style of an interactive threshold where we can identify our anomalous ice pixels compared to the average background. And then we go through and we specify a few options to help us vectorize. Here at this step of the workflow, and I'm going to pause the video for a second, we have an interactive table that lets us go through and we can manually perform QA/QC on the anomalies that have been identified. For this case, where we have hundreds of icebergs, it's a little laborious, but if you can imagine an image where you maybe have 25 or 50 anomalies overall, it's a great way to go through and filter out noise and make sure that you're focusing on what's important to you. Let me let the video finish here, which the last step that we've got is really just exporting our results as a vector. So once we specify the file and have our results generated, I'm going to pause again, and we can see nice little red outlines showing the pixels that represent icebergs. And this is a fun way that you can use anomaly detection, where our average pixel value represents water. So our anomalies are non-water pixels, or icebergs in this case. So those are two of our workflows at a little bit more of a glance. Let's take a look here at the most exciting part, or what I think is one of the most exciting parts of these workflows. So as you go through the steps of these workflows, the buttons you click on, the parameters you set, all of that information is tracked. And once you get to the very last step, there's this button that says Open Workflow in ENVI Modeler. When you click on that button, just like it shows here, we take our anomaly detection workflow, and then it creates an ENVI Modeler workflow of the exact same thing. This matches our input data and our parameters. This is a great way for people who aren't experts at the ENVI API or want a little bit of help generating the IDL code to automate their processes to get started. So if you have a lot of data sets you need to work through, this is a great tool to use. The ENVI Modeler allows you to generate IDL code as well. And if you've paid attention to some of our more recent releases, you can also send processing through the ENVI Modeler to ENVI Server in the background. So we'll talk a little bit more about the workflows here towards the end of the presentation. But for now, let's pivot to our next main topic, which is the temporal data cube. So our temporal data cube is a small but mighty feature. So there's a couple of ways that we're going to actually be introducing temporal data cube. We're going to talk about some of the changes that have been made to ENVI, and then we're going to walk through a real world use case for creating and analyzing a temporal data cube using machine learning. So with that, temporal data cube is a small but mighty change, as I mentioned. Effectively, we added a new metadata item, which allows multi-band rasters to have time associated with each band. This information then gets used across ENVI and is really accessed or generated mainly through the Build Temporal Cube tool, which you'll see on the right-hand side of our screen. In the Build Temporal Cube dialog, you can pick any number of rasters as long as they have time information. And optionally, you can specify a spectral index, which will be automatically calculated for you for each one of your data sets. This really helps automate the generation of a time series. The spectral index is optional. If you have single band rasters already, then you can just specify those as your input rasters, and this will create that temporal data cube for you. Once you have made a temporal data cube, let's take a closer look at some of the changes that have been made across ENVI to support this. Here we see the overall ENVI UI and a bunch of dialogues. The first one I want to draw your attention to is in the top left of the ENVI screenshot, where we have the data manager and a little bit of a peek at our layer manager. If you look closely, the band names that are shown are actually the collection dates in year, month, day format. Now, this is something that you can tweak or customize when you're creating the temporal data cube. And this is just what I picked here, which is the default. The second place that this time information is used is in the spectral profile. So now, if you use a spectral profile for an image that's a temporal data cube, it turns into a temporal profile. So you'll see that the title of our plot window in the lower left says temporal profile, and the horizontal x-axis reflects the date for each band and is appropriately spaced out. And lastly, if we look at our statistics view or our quick stats tool, the horizontal axis and band names within this tool also reflect the date as well. So these are all the places where we consume that time information when you're visualizing and taking a closer look at your data. So with that, let's pivot to our scenario that we're going to walk through today. So for our scenario, we are going to be working with 13 Cloud 3 mosaics using Sentinel-2 data from Earth on AWS. So here we have an animation that's made with ENVI's PowerPoint generation tools that just shows kind of our region of interest. So we've got a lot of crops and agriculture. And as we're going, we can see new plants or fields growing, becoming green. And then once they get harvested, that's cleared out and just looks kind of like barren ground or dirt. And so what we're going to walk through are the actual steps that I went through to accomplish this, how I went through discovering and accessing data, preparing it, and creating the temporal data cube. And then we're going to dive into machine learning, where I was attempting to map different harvest times, whether it's spring, summer, or fall for different types of crops. So first, let's jump to our first step of our workflow, which was data discovery. There are many tools that you can use to access Sentinel-2 data. Because I'm familiar with Sentinel-2 living up on AWS, I decided to use the Sentinel Hub EO browser. This handy tool lets you go through, find scenes of interest, get their location in Amazon's S3 buckets. This is data storage that's hosted up in the cloud. Then we can use these S3 URLs to automatically download the data and then consume that within ENVI. In total, when I was discovering data, I found 26 scenes with 13 different collection times. So basically, I have two east-west tiles, as shown in the screenshot here, where I'm downloading those two tiles at the same collection time, mosaicing them together, and that gives us one of our 13 overall scenes that we're using for our temporal data cube. So next, we're going to talk a little bit about how I actually went about downloading the data. Now, first things first, I don't want to scare anybody away by showing some code, but I am a programmer. And for me, programming is not just about creating cool workflows or analytics. It's about saving time and being a little bit more efficient when I've got a lot of things to do. And that's a great thing that you can use for accessing data and downloading it locally. So here we've got two screenshots that show some IDL code. On the left, we have all of our S3 URLs for the tiles of Sentinel data that we actually used for this analysis. In the middle, I have my IDL script that goes through each one of our S3 buckets and uses the AWS command line interface, or CLI, to actually download that locally. So it's not crazy, it's not rocket science, but it's much, much easier than going through and manually downloading each of the scenes. And I find that whenever I'm working with some sort of a time series project, getting the data, accessing, downloading it is always one of the things that you spend a lot of time on. And me personally, I love having the data locally on my hard drive. So it just makes me feel more comfortable. So that's part of why I did this. But once we have the data downloaded, it's actually really easy to work with. To actually build the temporal data cube and get our data ready for analysis, it's only about 25 or 30 lines of IDL code. On the right here, you'll see the program that I wrote to, once we had the data downloaded, to find all of our files, mosaic the images together, and then build the temporal cube. One of the things that's really nice, and something I skipped over accidentally, is that the data that I'm accessing is Sentinel level 2A, meaning that it's surface reflectance. So there's not any additional pre-processing or atmospheric correction that needs to be applied. It's ready to go. So that means we just need to open up our data sets, mosaic them together, which is what these 3 lines of code by my mouse are actually doing. So like I said, I'm a programmer. And when I think of programming, it's a great way to help automate and be more efficient. If you wanted to, yes, you could open up all of these images within ENVI and manually mosaic. But at the very least, I would strongly recommend, if you were going to go through this, is using the ENVI modeler. This is something that would be pretty easy to automate with the ENVI modeler as well, using mosaic and build temporal cube. So whether it's IDL or the ENVI modeler, there's plenty of ways that you can automate these processes and help save yourself some time and be a little bit more efficient. So anyways, let's have a look at what our temporal data cube actually looks like. So from the previous slide, you may not have noticed it. In my little code snippet, when I was creating the temporal data cube, I used NDVI as my spectral index. So here, as we go through, you can see some of the crops become brighter and then darker, which also most likely correspond to the growing season for a plant and then when it was harvested. If you look closely, you'll also see some of the vegetation near the mountains also has a little bit of seasonal variation as well. There's a few times that there's some clouds scattered across the mountains on the right side, but that's okay because we're really focused on the agricultural and urban areas on the left. So before we actually jump into our analysis, there's a very important step that we went through just as kind of verification. And this image isn't just about having a pretty picture that we showed very quickly earlier, but it's gaining a little bit of insight into the fields for this scene. So what you're looking at is an RGB color composite using 3 different times in our temporal data cube. We have an NDVI from spring, summer, and fall as the red, green, and blue components used to generate this image. These crazy colors that you see represent the health of vegetation over the course of year at 3 current times. These strong colors where you might have red, blue, green, or pink, or cyan can represent the times where we have harvest being in spring, summer, or fall, or some combination of the 3. So really, this is just kind of an extra step where we're not only making a pretty picture, but we're verifying that we can at least see, if we pick a couple of bands, we can see that NDVI does in fact change over the year. So with that, we kind of decided, or I had kind of decided that this is something we'd play around with machine learning to see if we could try and map when these crops were actually harvested. So with that, we used machine learning. So let's give a very brief introduction to some of the new machine learning algorithms that have been added for this ENVI release. We will talk about this more in just a few slides, so I'm not going to go into too much detail here. But at a very high level, we have 3 different classes of machine learning algorithms that have been added to ENVI. We have supervised, anomaly detection, and unsupervised. So for people who watched the machine learning webinar a few weeks ago, this probably looks familiar because this slide's from that presentation as well. For our temporal data cube, we actually used random forest over on the left in our supervised classification bucket. Very quickly, I'll say, you are going to get a copy of these slides so you can look at it later. But if you're wondering what the stars represent, that's kind of the Zach's recommended list of algorithms to use. 3 stars are the ones that I recommend just because they're kind of the easiest and they're very quick. There's plenty of other algorithms in here that you can play around with if you'd like to, but 3 stars are what I'd stick with. So anyways, for our scenario, we used random forest. So let's talk a little bit about our training data for machine learning and what we actually used for training data. So if you're familiar with deep learning, one of the important differences for machine learning and deep learning is that machine learning uses a pixel and all of the values for each band as training data and is actually processed when you're classifying an image. We're not looking at a pixel and all of its surroundings, which is most commonly what deep learning does. There's plenty of other flavors of deep learning, but at least with respect to ENVI, we're using convolutional neural networks for deep learning that look at a pixel and 90, 180, a couple hundred pixels around it, just like our eyes do. Machine learning does not work that way, though. Here, just like we see in our spectral profiles of some different harvest times that was captured throughout our data, machine learning just has access to our 13 different data points to be able to make decisions and determine if we're summer harvest, spring harvest, or maybe spring and fall harvest, depending on the growing season. And so because we are using Spectra, the way that we capture those spectra for use with machine learning is through ENVI regions of interest, or ROIs. So here you'll see a bunch of screenshots on the right side of the image. It's a little busy, but I just wanted to show some examples. So we've got the colors and names of the different regions of interest, and then just showing you where we've got or what some of the training data actually looks like. The main takeaway here is because we are using Spectra, we can use points, polylines, or polygons to actually capture the pixels that we want to use for each individual class. If you want to learn a little bit more about this, you can check out the machine learning webinar, which we'll talk about here in just a second. But for now, we're going to leave it at that. And once you have your regions of interest, it's very easy to go through, generate a machine learning or random forest model, and then process your data. So you have 3 different ways that you can actually do this in ENVI. First, you can use our toolbox entries, which I like to call easy peasy or one-shot tools, which you see on the left. You can specify your raster, our temporal cube, and then our regions of interest. Or similar to the ENVI workflows, you can click on the Open in Modeler button, which will then generate an ENVI Modeler workflow that you can customize and make your own, which is what I did here. So machine learning is just 3 simple steps. Get your training data from regions of interest, generate your random forest classifier, and classify your image. And if you are a programmer, last but not least, you can also execute this workflow from IDL. Here we're using the IDL code generated by the ENVI Modeler workflow that's just shown on the right. So plenty of easy ways to get into machine learning within ENVI. We have very simple and easy to use tools, but if you are more advanced and a programmer like me, you can take advantage of them that way as well. So with that, let's go ahead and take a look at our results here. So this is a very high level and just targeted at the harvest times during the year for fall, summer, and fall, summer, or spring. Our harvest analysis. So at first glance, you might say, wow, look at those pretty pictures. It did a great job. But one of the things that was kind of interesting as I was going through this exercise is I started really digging into the results to try to see if they were right or not by looking at the temporal profile of some of these different plots. And this is where I found that this is actually a pretty hard problem to solve. Primarily because not all of our signals are nice and clean and crisp, like I showed at the beginning. Here's a few examples of some temporal profiles that just bounced all over the place. And I couldn't even tell you if that was harvest or just noise. Maybe it's an orchard with, slight shift in the pixels where we've got, dark green vegetation for trees and space between them. I don't know. I'm not an expert at vegetation analysis. But what I can tell you is you probably want to take my results with a grain of salt there. But the exercise still remains, where we're showing that it's very easy to go through and with ENVI regions of interest, identify pixels that you care about, use the temporal profile to help you identify what class different pixels might belong to. And then once you've processed your image, I can then use the temporal profile as a little extra QA/QC to see if they actually match and make sense. And this really gets us, well, actually, I'll pause on that. We'll circle around to the machine learning workflow in just a second. So that's it for our kind of real world use case with temporal data cube and machine learning. Let's pivot to talk a little bit more about the machine learning algorithms themselves. as well. So just a little heads up, there's a few slides I may quickly go through just to keep us on track. We want to try to end by about the 40-minute mark of the hour, so we've got some room for questions. So what we want to focus on for this slide are just cover a few key points for machine learning and deep learning capabilities in ENVI. The first thing that I want to make sure to call out is that the machine learning algorithms in ENVI are free, do not require an extra license, apart from you needing to have ENVI 563 in order to access. One of the things that we want to make sure is very clear, though, is that the machine learning algorithms are bundled with the ENVI deep learning module. However, they do not require a license or module license feature in order to use. So anyone, if you go into the Download and Licensing Center, anyone should be able to see the ENVI Deep Learning 2.0 installer, download, run the installer, and have immediate access to machine learning. One other important difference between machine learning and deep learning is that for ENVI, machine learning uses the CPU, and deep learning requires an NVIDIA GPU. So machine learning is CPU, deep learning is NVIDIA GPU. Additionally, for machine learning, we have optimized libraries for Intel CPUs. AMD are also supported, but some of the algorithms are almost unusable. They're so slow unless you have an Intel chipset. So that's also one of the reasons that I recommend random forest or extra trees, because whether you have Intel or AMD, you still have very good performance with each. So next, I want to just show real quick how you can actually install and access the download for ENVI 563 or the machine learning tools within the deep learning installer. So starting in the top left of this slide, if you install ENVI 563, you'll have a kind of little dummy toolbox for machine learning with a single tool in it, which is install machine learning. If you run this tool, it'll open up a dialog that gives you a little bit of information about the machine learning capabilities, and has a handy button that if you click on will take you to our download and licensing portal to access the installer. Once you sign into the download and licensing portal, you will see ENVI Deep Learning 2.0 living alongside the ENVI 563 download, and you can download, install this, no need for an extra license or anything, as I mentioned. It's just separate because our machine learning and deep learning capabilities are quite large. That's how they're packaged, and we don't want to make the ENVI installer too big. So we've got a couple of more examples just showing machine learning within ENVI. This first one, and I'm only going to let the video play once just to keep us on time here. We're going to map where we have an active volcano looking at current and hot lava, flowing lava. And then we have blue representing where we've got previous lava flows. And we have this kind of pinkish purple color representing volcanic gas plumes in our image. So this is one example just to show. The other example, and this is one that I like a little bit more, and I'm going to let this play because this is doing processing real time. The previous video was sped up because it takes a few minutes. But here we're going to use machine learning for change detection. On the right of the image, you'll see yellow boxes and red boxes. The yellow boxes represent areas where we have a wildfire that's burned down a forest. This is from the Black Fire in New Mexico in the United States this past summer. And the red boxes identify areas where there's no change, where the ground has not been burned. And here we have two PlanetScope 4-band images that have been stacked together, and we're going to identify just those changed pixels. So this is a real-time video, as I said, it takes about 30 seconds to go through. I'm going to pause at the end here where we see these bright yellow pixels on the right that correspond to where we have our burned areas. It's not perfect. This was something I spent quite literally about 20 seconds drawing the bounding boxes for. But the good news is, with how crisp our boundaries are here, you could use something like classification aggregation to very easily remove all the noise and fill in the holes on the right-hand side of the image. So this is just another example, really trying to illustrate how quick you can use machine learning It literally takes 30 seconds or a minute, depending on how much training data and how big your image is, but it's something you can very quickly iterate over, which ties back to our original example with the temporal data cube, where even if my analysis wasn't great, because it's very quick to generate machine learning, classify, or process my image, I can iterate and tweak my training data and cycle through and do that a couple of times very quickly. Whereas with deep learning, it might take a couple of hours or even half a day or a whole day to generate a deep learning classifier, depending on how much training data you have. So last thing I want to call out for machine learning, we also support hyperspectral data. I'm going to go very quickly over this slide. I just want to call this out. If you want to learn a little bit more about our machine learning capabilities, we have a webinar that's up on our website right now, also hosted by JP and myself, where we go into all of the details, including the hyperspectral use case. If you go to l3harrisgeospatial.com and look at learn and then videos, you'll see that the video on the right here at the top of the list. So feel free to check that out if you'd like to learn a little bit more about machine learning. With that, let's pivot back to some of the features for ENVI and IDL, and I am going to go pretty quick just to keep us on time. So first, we want to talk about a few IDL routines that have been added. First one here is compile code. So previously, and if you're an IDL user, we've had the execute function. This is the compile code procedure, which allows you to dynamically define new procedures and functions at runtime in IDL. So previously, the execute function was limited to just single line statements, and now you can use single line statements in execute or define new functions or procedures using compile code. So being a little bit more open than we have in the past. Additionally, we have two new statistics routines, running stats and running covariance, which allow you to calculate statistics for large arrays using previous values as a starting point. This can help you save time and be more memory efficient than this has been in the past if you've got a lot of data to process and work through. Additionally, we've added some new IDL routines for encryption using RSA private and public key pairs. With this, you can create an RSA pair, and then you can encrypt a string like we've got in our example here. And then once you've encrypted it, you use the private key to decrypt. This is also a really exciting feature because adding this to IDL opens up the door for being able to store credentials within ENVI for remote data sets or remote things that you may be accessing that require credentials. All right, pivoting back to ENVI, here we have a couple of new data formats that we're introducing as well. We've added support for ENMAP, which is a German hyperspectral satellite mission on the left, and on the right, we've revamped our support for planet data. The Planet Explorer user interface, where you can search and download data from the planet catalog, has a couple of new options for selecting harmonized and clipped data sets. And we now support all of these being open natively within ENVI. So if you upgrade to the latest version of ENVI, you'll get the latest support for planet data as well. In addition to this, we've added a few more, more than a few spectral indices, 33 in total. We've added 6 new vegetation indices, and then 27, if I'm remembering the number right, for mineral indices. The important thing to note here is that the mineral indices, I believe, all require hyperspectral data in order to access or process or generate, because if they use narrowband wavelengths. We also have a new annotation type that's been added to ENVI, which is range rings. Here, if you look in the screenshots on the left-hand side of the image, you'll see from the annotation dropdown, you can select range ring, which allows you to specify one or more rings and then the distance associated with the numbers that you've specified. And then anytime you click through ENVI's display, it will add the rings just like it's shown here. These rings are a new annotation type and have properties, transparency, fill, stroke values that you can adjust. So here's just a couple of customizations that I applied just to showcase that they are separate entities that you can make and look however you want to, in case you'd like to have a little bit of fun with them. We've got a few more ENVI features to cover. Two notable items that we wanted to make sure to call out is that the point cloud feature extraction tool within ENVI has been updated. So the dialog on the left has parameters organized within a tab now, which makes it a lot more manageable to take a closer look at. Before, this was probably one of our more complicated tasks or user interface elements that we had. It's much more approachable now. And if you are someone who creates your own ENVI tasks, this is something that you can use yourself using ENVI style sheets. Then on the right here, another small but mighty change is that from the File Open World Data drop-down menu, you can now easily access SRTM DEM data from anywhere within ENVI. So if you have an image open and you want some data that's higher resolution than the global GM-TED data set that ships with ENVI, you can use your viewport bound and get a bounding box, which you'll see in the dialog there directly from ENVI's view. So it's very easy. Zoom into where you want on your image, open up this tool, and then wait a few minutes to download the data, and you'll be off to the races. And then lastly, additionally, we've added more ENVI tasks to this release. So this is excluding the machine learning tasks, which I think is around 20 or 30. We have 14 just base ENVI tasks that have been added. For those that aren't familiar with what ENVI tasks are, they're really our building block that's used to generate the workflows we showed earlier, ENVI modeler, and being able to access through IDL via the ENVI API. So I'm not going to go through all of these here, but just want to include this as a list. So I've got two more quick slides and then we'll get to questions. We have a couple of important breaking changes that we've introduced to this release with some of the new workflows and machine learning capabilities that we want to make sure everyone's aware of. First, we've gone through and cleaned up ENVI's toolbox a little bit because of the new ENVI workflows that have been added. Here you'll see the complete list of our legacy tools that have been removed, but we have replaced the functionality with our new ENVI workflows. So as I mentioned before, this is something that's going to be ongoing over the next couple of ENVI releases. We're going to be modernizing and giving new ENVI user experiences to some of the tools that have been around in ENVI for a while. So this will be something that's coming over the next couple of releases, but do keep in mind that the tools that we're going to be removing will have replacements with the existing functionality. Other breaking change we want to make sure to call out, and this is a lesser known feature that we have in ENVI, is the classification framework. So this was something that was added maybe 5 years ago as a way to use machine learning within ENVI. And it was a little clunky, a little bit hard to use, and that was one of the motivating factors for us adding in our new machine learning capabilities to ENVI, which is part of why you saw reimagined machine learning workflow on one of the slides earlier. So this is something that should not affect very many customers. And in fact, it's a great reason to switch over to the new machine learning tools as well, because they perform much better. And like I said, it's a dramatically easier and more modern user experience that I would expect you to have. So with that, we'll turn it back over to JP. We'll turn our cameras back on here and answer a few questions.
Fantastic. Great. Thank you, Zach, for the presentation on what's new in ENVI. At this point, we'll answer some of the questions that have come in. And as a reminder, you can send us questions in the Q&A chat box in the Zoom dashboard, and they'll show up live for me, and then we'll answer a few right now. So, Zach, in machine learning, and we might have had this question before, but it's good to reiterate it. Are we separating the imagery into training and validation like we did in deep learning, or is that changed?
Great question. So for machine learning, we actually don't split it into test and validation. If that's one of the things that you would certainly be interested in seeing in part of the machine learning tools, maybe evaluating performance against kind of a test data set, we'd be more than happy to add that in. We didn't add that for machine learning, kind of for two reasons, just to explain it very quickly. Is for the most part, when you generate a machine learning classifier, such as random forest, you get pretty amazing performance with regards to your training data. And the way that I most commonly see how the data set is actually performing is I will classify a new image that didn't have any spectra as part of the training data. Because that way you can see, tens of millions of air quotes examples and how they actually perform. So part of that's a little bit biased because of how I've gone through and actually used machine learning, where I'm actually looking at imagery as a good way, to understand how the performance is. But I know that different people have different approaches. So like I said, if that's something you'd be interested in, feel free to let us know.
Okay. All right. I have a super technical question, Zach, and it's pertains to support vector machine. It says, in general, there are 3 parameters needed to be set for SVM regression: epsilon, kernel, and penalty. In the current IDL version, we can only set kernel and penalty. How can I set epsilon? And if we can't, what is the default value used?
That's a good question, and I don't know that off the top of my head. You are more than welcome to use SVM if you would like to, but if I pull up my slide here where I have kind of my recommended machine learning algorithms, this is actually one that I don't really recommend to use within ENVI or ENVI machine learning because it is so slow. So if you don't have an Intel CPU, this is one that's almost unusable, where in some of our initial time testing, it was taking more than 30 or 60 minutes. We actually stopped our time test because there was no progress, and random forest and extra cheese performed very quickly. So I just want to shout that out with regards to SVM, but feel free to use it if you want to. Like I said, those are just my recommendations. I don't know about the specifics for parameters. If we had a little bit more time, I'd open up ENVI and open up the tools here for SVM just to have a closer look. I think the Doc Center should be updated, so you might be able to Google SVM classifier within ENVI, and you should hopefully find our new docs page on that, which might give you an answer. If not, you can feel free to send me an email, and I'll figure that out for you.
Absolutely. And yeah, don't be afraid to send an email to us to start engaging on that front for technical questions like that. Zach, do you want to put up the contact again real quick?
Sure.
And then here's some softball ones. Is there support for Prisma? We saw that we have support for Nmap.
Great question. And if I remember, if I remember correctly, is Prisma the
Hyperspectral satellite?
Italian hyperspectral satellite. I feel like we've already got support for that within ENVI. I think we added that in the last release. Just real quick, and you're probably going to laugh at me for this. ENVI, if you Google something along the lines of ENVI data format support, you'll see supported file types here. And I think if we do a search for Prisma, yep, we'll see that already. So in case you're wondering, if you just Google ENVI data format support, just like I did here, I have to do that occasionally to get a little bit, to make sure I'm right about things. So Prisma is supported.
Fantastic. And along the same lines, another question is, for those new mineral indices, are the way that they're actually done, is that in our help file?
Yep. All of our spectral indices will be in our help. And this is also how I find this. If you Google ENVI, spectral indices, this will give you our doc center for spectral indices. And there should be a alphabetical list of spectral indices, which you can also look at for, I think, the mineral indices themselves, which if we dig in here, we can get like the alunite index, for example, which this gives you the specific wavelengths that are used in there and gives you the reference paper for that as well.
Perfect. So somebody can look that up if they want to actually see the research that went into it. Perfect.
Yep.
Very. Go ahead, Zach. What were you going to say?
Oh, very easy to find.
Exactly. And the last question we have, and this is pertains to IDL. Zach, can you tell us the difference between compile code and execute function?
Yes. So for our IDL programmers out there, let me pull this up again. So compile code is very specific in what it does. It will simply compile the code, and if there's any functions or procedures, it will add those to IDL's internal lookup of routines that are present. It will not actually run anything that such as main level programs. It only defines functions and procedures. If there's something that you want to actually run dynamically, that's where execute will come in. So for example, the first thing I did when I got this was I had a function I defined, and then I had a main level program at the bottom of it, and I was trying to run the main level program, and that doesn't work because that's not how it was designed to. So it simply defines functions, and then you can call them like I have right here.
All right. I like how the contrast is turned way up in the code colorization right there.
Oh,
all right, with that, I was going to say we've taken care of all the questions. Let's wrap things up. We appreciate everybody's attention on the line, and thank you again, Zach.